Good morning everyone. Welcome to the course Stability Aspects of Structural Steel Design, Concepts and Applications. Let us continue our conversation on plate buckling. Today we will talk about plates with different loading and boundary conditions. In the previous class, we learned that the solution for critical loads for plates using energy method comes from the total potential energy of the plate, which is a combination of strain energy due to bending of the plate as well as the potential energy due to externally applied loads V. So, the strain energy due to bending U is given as U equal to d by 2 double integral of 0 to b 0 to a dou square w by dou x square the whole square plus dou square w by dou y square the whole square plus 2 into mu into dou square w by dou x square into dou square w by dou y square plus 2 into 1 minus mu into dou square w by dou x dou y the whole square bracket close dx dy. The potential energy due to external loads V is given as, for all four sides simply supported, V equal to minus half into 0 to a nx into dou w by dou x the whole square into dx into dy. Here the double integral is 0 to a and 0 to a simply because it is considered as a square plate. Both the length of the plate and the width of the plate is given as a. Now, when we have plate that is subjected to biaxial bending, we have V equal to minus 1 half into 0 to a nx into dou w by dou x the whole square into dx into dy minus 1 half into 0 to a ny into dou w by dou y the whole square into dx into dy. Here we are taking account of the fact that the plate is subjected to biaxial compression. So, for compression in x direction we take Nx, and for compression in y direction we take Ny, and hence the equation gets repeated twice. The first part of the equation corresponds to the compression in the x direction, and the second part of the equation, that is in black color, corresponds to the compression in the y direction. Now, let us compare the critical load for uniaxial as well as biaxial compression. So, for plate under biaxial uniform compression, we have N critical given as 2 pi square d by a square, where k is the elastic plate buckling coefficient given as 2.0, and for plate under uniaxial uniform compression we have Nx equal to 4 pi square d by b square, where the elastic plate buckling coefficient is given as 4.0. So, we can see that when the plate is compressed only in one direction, it is twice the load that is carried by when the plate is compressed in both the directions. Therefore, the uniaxial compression has twice the load carrying capacity of a plate compared to a plate that is subjected to biaxial compression. Now, let us talk about a plate that is subjected to uniaxial compression, but in this case all the four sides are fixed. So, you can see the loading conditions here, which is uniaxial compression, and the boundary conditions are all four sides fixed. The length of the plate is given as a and the width of the plate is also given as a, which means that it is a square plate. So, let Nx be the uniformly distributed force acting along two opposite edges, and the boundary conditions is given as at x equal to 0 and x equal to a, the lateral deflection W is equal to 0 and the slope dou W by dou x is equal to 0. Similarly, at y equal to 0 and y equal to a, the lateral deflection W is given as 0 and the slope is given as dou W by dou y is equal to 0. Now, assuming that the function for lateral deflection to be W equal to a into 1 minus cos 2 pi x by a into 1 minus cos 2 pi y by b. Let us check if this function satisfies the boundary conditions. So, at x equal to 0 and x equal to a, we have the lateral deflection W is equal to 0. At x equal to 0, W equal to a into 1 minus cos 2 pi into 0 by a into 1 minus cos 2 pi y by a, which is equal to 0. How do we get that 0? We know cos 0 equal to 1. So, 1 minus 1 is equal to 0, and hence at x equal to 0, W equal to 0. Similarly, at x equal to a, W is given as a into 1 minus cos 2 pi into a by a into 1 minus cos 2 pi y by a. We know that cos 2 pi equal to 1. So, 1 minus 1 again becomes 0, and hence W equal to 0. Now, the slope dou W by dou x is equal to 0. So, when we differentiate that and substitute x equal to 0, dou W by dou x is given as 2a pi by a into sin 2 pi into 0 by a into 1 minus cos 2 pi y by a. We know that sin 0 equal to 0. So, hence dou W by dou x is equal to 0. Similarly, at x equal to a, dou W by dou x is given as 2a pi by a into sin 2 pi a by a into 1 minus cos 2 pi y by a. We also know that sin n pi equal to 0, here sin 2 pi is there and hence this also becomes 0. And let us substitute at y equal to 0 and y equal to a, the latter deflection w equal to 0, and when we substitute y equal to 0, again w equal to a into 1 minus cos 2 pi x by a, which remains same, and the next term 1 minus cos 2 pi 0 by a, which becomes 0 simply because cos 2 pi becomes 1 and 1 minus 1 becomes 0. And at y equal to a, w equal to a into 1 minus cos 2 pi x by a into 1 minus cos 2 pi a by a, and again cos 2 pi equal to 1, so 1 minus 1 becomes 0. And now let us look at the slope dou w by dou y equal to 0. So when we have y equal to 0, dou w by dou y is given as 2a pi by a into 1 minus cos 2 pi x by a into sin 2 pi into 0 by a, again sin 0 equal to 0, so the entire term becomes 0. Similarly, when we substitute y equal to a, we have dou w by dou y equal to 2a pi by a into 1 minus cos 2 pi x by a, which remains the same, and this time we have sin 2 pi into a by a. We know that sin n pi equal to 0, so sin 2 pi is also 0 and hence the term also becomes 0, which means that the function satisfies all the boundary conditions and we can proceed to calculate the critical load. So the total potential energy of the plate is given as strain energy due to bending U and potential energy due to external loads V. So the strain energy due to bending, as we have seen already, U equal to d by 2 into double integral of 0 to a dou square w by dou x square the whole square plus dou square w by dou y square the whole square plus 2 mu into dou square w by dou x square into dou square w by dou y square plus 2 into 1 minus mu into dou square w by dou x dou y the whole square into dx into dy. Now we can expand this integral by including each term under the double integral terms, as you can see here, and this we do it for one simple reason, because we can split this big equation into 4 small equations, because they all have 4 small integrals in this one. So we have split this equation, as you can see, as 1, 2, 3 and 4. Now to evaluate this expression, the following derivatives are needed. So we have w equal to a into 1 minus cos 2 pi x by a into 1 minus cos 2 pi y by a. So we have dou w by dou x equal to 2a pi by a into sin 2 pi x by a, because when we differentiate 1 it becomes 0 because 1 is a constant. When we differentiate cos it becomes sin, especially minus sign. We already have a minus there, so minus into minus becomes plus, and the constant 2 pi by a is remaining. So we have this 2a pi by a into sin 2 pi x by a into 1 minus cos 2 pi y by a. Because it is a partial derivative, the y terms remain unaffected and it is simply kept there. Now when we differentiate it twice, we have dou square w by dou x square, which becomes 4a into pi square by a square into cos 2 pi x by a into 1 minus cos 2 pi y by a. Similarly, when we do so for w equal to a into 1 minus cos 2 pi x by a into 1 minus cos 2 pi y by a, when we partial differentiate it with respect to y, we have 2a pi by a into 1 minus cos 2 pi x by a into sin 2 pi y by a. The same explanation that is given for the first derivative is also applicable here, because the constant 1 is 0 when we differentiate it, and then cos becomes minus sign. We already have a minus there, so minus into minus becomes plus, and then it becomes sin into 2 pi into y by a, and this 2 pi by a actually is a constant that can be seen here in the front side of the equation. When we differentiate it twice, that is dou square w by dou y square, we have 4a into pi square by a square into 1 minus cos 2 pi x by a into cos 2 pi y by a. And similarly, when we double differentiate it with respect to dou square w by dou x dou y, we get 4a into pi square by a square into sin 2 pi x by a into sin 2 pi y by a. Now let us evaluate the integral 1, which is 0 to a dou square w by dou x square the whole square into dx into dy. When we do so, we expand this equation when we substitute dou square w by dou x square as 4 into a into pi square by a square into cos 2 pi x by a into 1 minus cos 2 pi y by b. So when we do so, we have 16a square into pi power 4 by a power 4 into 0 to a cos into 2 pi x by a the whole square into 1 minus 2 into cos 2 pi y by b plus cos 2 pi y by b the whole square into dx into dy. What we have simply done is that the cos term basically remains the same. So, cos 2 pi x by a becomes cos 2 pi x by the whole square because its square term is there. The next term 1 minus cos 2 pi y by b, basically it is treated as a minus b the whole square. So, we have a square minus 2ab plus b square, which is expanded and it is shown on the right hand side of the equation. So, when we simplify this further, we have that 16a square into pi power 4 divided by a power 4 into 0 to a cos into 2 pi x by a the whole square minus 2 into cos 2 pi x by a the whole square into cos 2 pi y by a plus cos 2 pi x by a the whole square into cos 2 pi y by a the whole square. Basically, we are taking this cos 2 pi x by a the whole square inside the bracket terms where we have expanded a minus b the whole square and we get a big term. And then now we can simplify this further by splitting this double integral into two single integrals, which becomes much easier, and so we get 16 into a square into pi power 4 by a power 4 into 0 to a cos into 2 pi x by a the whole square into dx into 0 to a dy minus 2 into 0 to a cos 2 pi x by a the whole square into dx into 0 to a cos 2 pi y by a into dy plus 0 to a cos 2 pi x by a the whole square into dx multiplied by 0 to a cos 2 pi y by a the whole square into dy. To simplify this, we can use the expressions that are given at the bottom, which is 0 to a cos 2 pi x by a the whole square becomes a by 2 and 0 to a cos 2 pi y by a the whole square also becomes a by 2, and the integral of 0 to a cos 2 pi x by a becomes 0 and integral of 0 to a cos 2 pi y by a into dy also becomes 0. So, when we substitute these values here, we get a much simplified equation, and the final value is 16 into a square pi power 4 by a power 4 into 3a square by 4. When we simplify this further, we get 12 pi power 4 into a square by a square. The second integral is 0 to a dou square w by dou y square the whole square into dx into dy. Now, when we substitute the value of dou square w by dou y square as 4a into pi square by a square into 1 minus cos 2 pi x by a into cos 2 pi y by a the whole square, we do the similar exercise that we have done in the first integral. We are expanding the term 1 minus cos 2 pi x by a as a square minus 2ab plus b square, and then we are taking this cos 2 pi by a the whole square term inside. So, we get a bigger equation here, and you can see that this again can be done the same way as we have done previously. We split these two double integrals into two single integrals. Now, we can simplify this further by taking advantage of the values that are given at the bottom of the screen, and when we substitute these values similar to what we have done previously, we get a value of 12 into pi power 4 into capital A the whole square divided by small a the whole square. Here the capital A is a constant and the small a is basically the length of the plate. In this case, it is also the width of the plate because it is a square plate. So, the third integral is 0 to a 2 mu into dou square w by dou x square into dou square w by dou y square into dx into dy. So, when we expand it, we get 0 to a 2 mu into 4a into pi square by a square into cos 2 pi x by a into 1 minus cos 2 pi y by a, and the next term is 4 into a into pi square by a square into 1 minus cos 2 pi x by a into cos 2 pi y by a into dx into dy. Again, we are using algebra here. When we do so, we get this one multiplied. So, 4a into 4a becomes 16a square into pi power 4 divided by small a power 4, and we have 2 here already in front of this equation. So, when we do so, we get 32 mu into a square pi power 4 by small a the whole power 4, 0 to a integral into cos 2 pi x by a minus cos square 2 pi x by a into cos 2 pi y by a minus cos square 2 pi y by a into dx into dy. Now, we can again split this into two separate single integrals. So, we have this integral 0 to a split in terms of dx, and the next one is split in terms of dy, which makes life simpler by using those values that is given at the bottom of the screen. So, when we do so, we know that cos into 2 pi x by a becomes 0, and then cos square 2 pi x by a becomes a by 2. So, when we do so, we get a much simplified equation here. As you can see, it becomes 8 mu into a square into pi power 4 by a square. So, the fourth integral is 0 to a 2 into 1 minus mu into dou square w by dou x dou y the whole square into dx into dy. So we know that dou square W by dou x dou y is given as 4a into pi square by a square into sine 2 pi x by a into sine 2 pi y by a, and when we substitute this, we have this equation 0 to a 1 minus mu into 32 a square into pi power 4 by a power 4 into sine square 2 pi x by a into sine square 2 pi y by a dx into dy. Again, we can simplify this further, and by splitting this double integral into two single integrals, we get the value 1 minus mu into 32 a square into pi power 4 by a power 4 into a by 2 into a by 2. Now, that gives you the value here, which is 8 a square into 1 minus mu into pi power 4 by a square. So, the first integral is given as 12 pi power 4 a square by a square, second integral is given as 12 pi power 4 into a square by a square, the third integral is 8 mu into pi power 4 a square by a square, and the fourth integral is given as 8 a square pi power 4 into 1 minus mu by a square. So, we can substitute this back into this strain energy of the plate equation, and we get this following equation, u equal to d by 2 into the equation that is given here, 0 to a dou square w by dou x square the whole square into dx into dy, plus 0 to a dou square w by dou y square the whole square into dx into dy, plus 0 to a 2 mu into dou square w by dou x square into dou square w by dou y square into dx into dy, plus 0 to a 2 into 1 minus mu into dou square w by dou x dou y the whole square into dx dy. So, when we plug all these values and simplify this further, we get some terms that are getting cancelled, as you can see here, and the final value boils down to 16 pi power 4 a square d by a square. Now, let us evaluate the potential energy due to external loads V, which is given as minus n by 2 into 0 to a dou w by dou x the whole square into dx into dy. So, when we do so, we get minus n by 2 into 0 to a 2 a pi by a into sine 2 pi x by a into 1 minus cos 2 pi y by a into 1 minus cos 2 pi y by a the whole square into dx into dy. So, when we do so, we can expand this equation. Again, we have this sine 2 pi x by a becomes sine square 2 pi x by a into 1 minus cos 2 pi y by a the whole square becomes a square minus 2ab plus b square. We can see this expansion as shown in the screen. So, we can expand this, we can multiply this, and we get the value based on the integrals that are given at the bottom of this one. We have minus 4 into a square into pi square by a square into n by 2 into this term sine square 2 pi x by a becomes a by 2, and the next term becomes a, and then we have minus a by 2 into 0 because cos 2 pi x by a becomes 0, and then the third term is 0 to a sine square 2 pi x by a becomes a by 2, and then 0 to a cos square 2 pi x by a also becomes a by 2. So, when we get this value, the value is given as minus 4 into a square into pi square by a square into n by 2 into 3 a square by 4. We simplify this further, we get the potential energy equation as minus 3 a square pi square n by 2. So, the total potential energy is given as u plus v. We have 16 d pi power 4 by a square divided by a square minus 3 a square pi square n by 2. Now, in accordance with the concept of neutral equilibrium and the principle of stationary potential energy, the critical loading can be determined by finding the slightly bent configuration for which the total potential energy has a stationary value, which basically means that when we differentiate it with respect to a, it should be equal to 0, and when we differentiate it with respect to a, that is partial differentiation with respect to a here in this case it is the constant. We have 16 d pi power 4 into a square by a square minus 3 a square into pi square into n critical by 2 a square, which is equal to 0. So, when we differentiate a square, which is capital A square, we get 2a, and similarly when we do the simplification, we get 32 pi power 4 d by a square equal to 3 pi square NCR. Our objective is to find out the critical buckling load. So, NCR is equal to 32 into pi square d by 3a square. So, we get n critical equal to 32 pi square d by 3a square. Now, let us solve the problem whose plate boundary conditions are simply supported on all four edges and it is subjected to a shear load, as you can see from the picture. Let Nxy be the shear force acting along pair of two opposite edges. The boundary conditions are at x equal to 0 and at x equal to a, the lateral deflection equal to 0, the moment dou square w by dou x square is also equal to 0. Similarly, at y equal to 0 and y equal to b, the lateral deflection w equal to 0 and the moment dou square w by dou y square is equal to 0. Assume the function for lateral deflection to be w equal to a1 into sin pi x by a into sin pi y by b plus a2 into sin 2 pi x by a into sin 2 pi y by b. Check if the function satisfies the boundary conditions. At x equal to 0 and at x equal to a, the lateral deflection w equal to 0. At x equal to 0, we have w equal to a1 into sin pi of 0 by a into sin pi y by b plus a2 into sin 2 pi of 0 by a into sin 2 pi y by b, which is equal to 0. Next, at x equal to a, we have w equal to a1 into sin pi of a by a into sin pi y by b plus a2 into sin 2 pi a by a into sin 2 pi y by b, which is also equal to 0. Now, we have moment dou square w by dou x square equal to 0. So, we have at x equal to 0, dou square w by dou x square is given as minus a1 into pi square by a square into sin pi of 0 by a into sin pi y by b minus a2 into 4 pi square by a square into sin 2 pi of 0 by a into sin 2 pi y by b, which is also equal to 0. Now, when we have at x equal to a, we have dou square w by dou x square equal to minus a1 into pi square by a square into sin pi of a by a into sin pi y by b minus a2 into 4 pi square by a square into sin of 2 pi a by a into sin 2 pi y by b, which again is equal to 0. Now, let us look at the second boundary, which is at y equal to 0 and y equal to b. We have the lateral deflection w equal to 0. So, at y equal to 0, we have w equal to a1 into sin pi x by a into sin pi of 0 by b plus a2 into sin 2 pi x by a into sin 2 pi 0 divided by b, which again is equal to 0. Next, we have at y equal to b, w equal to a1 into sin pi x by a into sin pi b by b plus a2 into sin 2 pi x by a into sin 2 pi b by b, which again is equal to 0. Now, the moment is dou square w by dou y square equal to 0. So, at y equal to 0, dou square w by dou y square is given as minus a1 into pi square by b square into sin pi x by a into sin pi of 0 by b minus a2 into 4 pi square by b square into sin 2 pi x by a into sin 2 pi 0 divided by b, which again is equal to 0. In all these functions, when we put sin 0 as 0, we get 0, and then in all these functions, when we substitute the value of 0, sin of 0 is equal to 0 and also sin of pi, 2 pi, 3 pi up to n pi is equal to 0. Hence, we get these values as 0. Next, look at y equal to b, dou square w by dou y square equal to minus a1 into pi square by b square into sin pi x by a into sin pi of b by b minus a2 into 4 pi square by b square into sin 2 pi x by a into sin of 2 pi b by b, which again is equal to 0. Now, the strain energy is given as U equal to d by 2 into 0 to a, 0 to b, dou square w by dou x square the whole square plus dou square w by dou y square the whole square plus 2 mu into dou square w by dou x square into dou square w by dou y square plus 2 into 1 minus mu into dou square w by dou x dou y the whole square dx dy. Now, evaluating each integral in the above expression, we have w equal to a1 into sin pi x by a into sin pi y by b plus a2 into sin 2 pi x by a into sin 2 pi y by b. Now, when we differentiate it, we get dou w by dou x equal to a1 into pi by a into cos pi x by a into sin pi y by b plus a2 into 2 pi by a into cos 2 pi x by a into sin 2 pi y by b. When we differentiate it again, we have dou square w by dou x square equal to minus a1 into pi square by a square into sin pi x by a into sin pi y by b minus a2 into 4 pi square by a square into sin 2 pi x by a into sin 2 pi y by b. We need to do so because the first integral is given as dou square w by dou x square the whole square. So, when we have this dou square w by dou x square the whole square, we put the entire dou square w by dou x square it, and when we square it and we expand it, we get a big term as it is shown here, and then we introduce the integral 0 to a, 0 to b, dou square w by dou x square the whole square into dx into dy, and using the definite integrals given here at the bottom, which is 0 to a sin square pi x by a equal to a by 2 and 0 to a sin pi x by a into dx equal to 0. So when we substitute that, we get a1 square into pi power 4 divided by a power 4 into a by 2 into b by 2 plus a2 square into 16 pi power 4 by a power 4 into a by 2 into b by 2 plus 2a1 a2 into 0. So the first integral is given as a1 square into pi power 4 b divided by 4a cube plus a2 square into 4 pi power 4 into b divided by a cube. Now let us look at this second integral, which is dou square w by dou y square the whole square. So when we do so, we differentiate it with respect to y the first time. We have dou w by dou y equal to a1 into pi by b into sin pi x by a into cos pi y by b plus a2 into 2 pi by b into sin 2 pi x by a into cos 2 pi y by b. So we have dou square w by dou y square equal to minus a1 into pi square by b square into sin pi x by a into sin pi y by b minus a2 into 4 pi square by b square into sin 2 pi x by a into sin 2 pi y by b. So we have dou square w by dou y square the whole square equal to minus a1 into pi square by b square into sin pi x by a into sin pi y by b minus a2 into 4 pi square by b square into sin 2 pi x by a into sin 2 pi y by b. When we square it, we use the formula a plus b the whole square equal to a square plus b square plus 2ab. When we expand it, we get a much bigger term, as you can see here, and we introduce the integral, which is 0 to a, 0 to b, dou square w by dou y square the whole square into dx into dy, and we get the term that is shown here at the bottom of the screen, and we substitute the values for the definite integral shown at the bottom, which is 0 to a sin square pi x by a equal to a by 2 and 0 to a sin pi x by a equal to 0. When we do so, we get a1 square into pi power 4 divided by b power 4 into a by 2 into b by 2 plus a2 square into 16 pi power 4 by b power 4 into a by 2 into b by 2 plus 2a1 a2 into 0. The second integral becomes a1 square into pi power 4 a divided by 4 b cube plus a2 square into 4 pi power 4 a by b cube. Next, let us look at the third part, which is dou square w by dou x square into dou square w by dou y square. So when we have this one, we already know that dou square w by dou x square equal to minus a1 into pi square by a square into sin pi x by a into sin pi y by b minus a2 into 4 pi square by a square into sin 2 pi x by a into sin 2 pi y by b. Similarly, we have dou square w by dou y square equal to minus a1 into pi square by b square into sin pi x by a into sin pi y by b minus a2 into 4 pi square by b square into sin 2 pi x by a into sin 2 pi y by b. So when we multiply the two, we get a much bigger term here, as you can see on the picture, and then we simplify this further, and when we substitute the integrals, we have a much bigger equation, as you can see at the bottom of the page, and the definite integrals are given as 0 to a sin square pi x by a equal to a by 2 and 0 to a sin pi x by a into dx equal to 0. So when we do so, we have a1 square into pi power 4 divided by a square b square into a by 2 into b by 2 plus a1 a2 into 20 pi power 4 divided by a square b square and multiplied by a bunch of zeros plus a2 square into 16 pi power 4 divided by a square b square into a by 2 into b by 2. So we have the third integral as a1 square into pi power 4 divided by 4ab plus a2 square into 4 pi power 4 divided by ab. Now let us look at the fourth integral, which is dou square w by dou x dou y the whole square. So we know that dou w by dou x equal to a1 into pi by a into cos pi x by a into sin pi y by b plus a2 into 2 pi by a into cos 2 pi x by a into sin 2 pi y by b. So when we differentiate it one more time with respect to y, we have dou square w by dou x dou y equal to a1 into pi square by ab into cos pi x by a into cos pi y by b plus a2 into 4 pi square by ab into cos 2 pi x by a into cos 2 pi y by b. So we have dou square w by dou x dou y the whole square. When we square it, we have a1 into pi square divided by ab into cos pi x by a into cos pi y by b plus a2 into 4 pi square by ab into cos 2 pi x by a into cos 2 pi y by b the whole square. So now we use the term a plus b the whole square equal to a square plus b square plus 2ab by squaring it, and we get a much bigger equation, as you can see on the picture. And when we substitute the definite integral values, we can solve this further, and we have this equation finalized values are given as a1 square into pi power 4 divided by a square b square into a by 2 into b by 2 plus a2 square into 16 pi power 4 divided by a square b square into a by 2 into b by 2 plus 0. So, we have a1 square into pi power 4 divided by 4ab plus a2 square into 4 pi power 4 divided by ab, and that is the fourth integral value. Now, let us substitute the above integrals into the strain energy equation u. We get a much bigger equation as you can see here. We can simplify this further. Some of the terms gets cancelled as you can see here, and a much simplified equation can be seen, and this can be much more simplified as you can see here. And then once we simplify it, we get the value d by 2 into pi square a square plus pi square b square the whole square into a1 square divided by 4a cube b cube plus 4a2 square divided by a cube b cube. And this can be again simplified as you can see here, u equal to d by 2 into pi square a square plus pi square b square the whole square divided by 4a cube b cube into a1 square plus 16a2 square. Now, let us look at the potential energy due to in-plane shear loading V, which is given as V equal to half into 2nxy into 0 to a, 0 to b, dou w by dou x into dou w by dou y into dx into dy. Now, when we substitute that, we get a much bigger equation as you can see here. This again can be simplified using the definite integral shown at the bottom of the screen, and then we get a number of equations that are equal to 0. The one that has both sine term as well as the cos term, which has the same values inside the bracket, gets 0. So, you can see that integral of 0 to a cos m pi x by a into sin m pi x by a into dx is equal to 0. However, when the terms inside the bracket for sine term and the cos term are different, we have 0 to a sin 2 pi x by a into cos pi x by a into dx is given as 4a by 3 pi. Similarly, we have integral of 0 to a cos 2 pi x by a into sin pi x by a into dx equal to minus 2a by 3 pi. So, when we use these values, we can simplify the above equation further as you can see here. Again, to reiterate, when the terms inside the sine as well as the cos are the same, the value of the integral is 0. When it is not the same, when it is different, one is twice the other, we have 0 to a sin 2 pi x by a into cos pi x by a. Here, the cos term is actually half of the sine term, or the sine term is twice the cos term. We have the value 4a by 3 pi, and when the cos term is twice the sine term, as you can see here, integral of 0 to a cos 2 pi x by a into sin pi x by a into dx is given as minus 2a by 3 pi. So, we substitute these above values and we simplify this further. As you can see here, the final value is given as minus 32 by 9 into a1 into a2. So, we have V equal to 1 half into 2nxy into 0 to a, 0 to b, dou w by dou x into dou w by dou y into dx into dy. So, we have V equal to minus 32 by 9 into a1 into a2 into nxy. We know that the total potential energy is given as u plus v. So, we have u plus v equal to d by 2 into pi square a square plus pi square b square the whole square divided by 4a cube b cube into a1 square plus 16a2 square minus 32 by 9 into a1 into a2 into nxy. Now, let x equal to pi power 4 d by 8 into a square plus b square the whole square divided by a cube b cube, and y equal to 32 by 9 into nxy. So, we can simplify this further. We have u plus v equal to x into a1 square plus 16a2 square minus y into a1 into a2. In accordance with the concept of neutral equilibrium and the principle of stationary potential energy, the critical loading can be determined by finding the slightly bent configuration for which the total potential energy has a stationary value. Now, when we differentiate that with respect to A, the total potential energy is given as dou u plus v divided by dou a1 equal to x into 2a1 minus y into a2 equal to 0. And similarly, dou u plus v divided by dou a2 equal to x into 32a2 minus y into a1 is equal to 0. So, arranging the equations in the form of matrix, we have 2x minus y 32x is equal to 0. So, we have 64x square minus y square equal to 0. So, 64x square equal to y square. We have 8x equal to y. Now, resubstituting x and y values, we have 8 into pi power 4 divided by 8 into a square plus b square the whole square divided by a cube b cube equal to 32 by 9 nxy. So, now nxy equal to 9 by 32 into pi power 4 d into a square plus b square the whole square divided by a cube b cube. And now, if a equal to b, we have nxy equal to 9 by 32 pi power 4 d into a square plus a square the whole square divided by a cube into a cube, which again simplifies to the value of 9 by 8 pi square into pi square d by a square. This 9 by 8 can be simplified as 11.1. So, the critical load Nxy critical equal to 11.1 into pi square d by a square. However, using a more precise analysis than the one presented here, Stein and Neff obtained for the critical load the value 9.34 pi square d by a square. Now, the load is given as Nx equal to N0 into 1 minus alpha into y by b. Here alpha is the stress gradient. So, when alpha equal to 0, we have Nx equal to N0, which represents the uniform compression. When alpha equal to 1, we have Nx equal to N0 into 1 minus 0 when y equal to 0, which becomes N0 at the top, and Nx equal to N0 into 1 minus of 1 into b by b, which becomes 0. So, Nx equal to 0 at the bottom. So, this leads to a triangular variation when alpha equal to 1. When alpha equal to 2, we have at the top 0 because Nx equal to N0 into 1 minus of 2 into 0 by b, which becomes 0. So, Nx equal to N0 at the top, and when we put the value of 2, we have Nx equal to N0 into 1 minus of 2 into b by b. So, 1 minus 2 becomes minus 1. So, this leads to a pure flexure case where there is a triangular load that is happening at the top, which is compressive in nature, and there is a triangular load that happens at the bottom, which is tensile in nature, as you can see from the picture, generic picture that is given here. Now, let us go through step by step. Let Nx be the distributed force acting along two opposite edges. The boundary conditions are at x equal to 0 and at x equal to a. We have lateral deflection W equal to 0. The moment is given as dou square W by dou x square equal to 0. Similarly, at y equal to 0 and y equal to b, we have lateral deflection W equal to 0 and moment is given as dou square W by dou y square equal to 0. Assume function for lateral deflection to be W equal to a sin pi x by a into sin pi y by b. Check if the function satisfies the boundary conditions. At x equal to 0 and at x equal to a, we have lateral deflection W equal to 0. At x equal to 0, W equal to a sin pi of 0 by a into sin pi y by b, which is equal to 0. At x equal to a, W equal to a into sin pi of a by a into sin pi y by b, which again equal to 0 because sin pi is equal to 0. And the moment is given as dou square W by dou x square equal to 0. Similarly, when we differentiate it twice, again it is a function of sine. So, we have dou square W by dou x square equal to minus a into pi square by a square into sin pi of 0 by a into sin pi y by b, which again is equal to 0. So, when we substitute at x equal to a, we have minus a into pi square by a square into sin pi of a by a into sin pi y by b, which again equal to 0 because sin pi equal to 0. Now, at y equal to 0 and y equal to b, we have the lateral deflection W equal to 0. So, at y equal to 0, we have W equal to a sin pi x by a into sin pi of 0 by b, which is equal to 0. Now, we have at y equal to b, W equal to a sin pi x by a into sin pi b by b, which is again equal to 0 because sin pi equal to 0. The moment is given as dou square W by dou y square equal to 0. So, we have at y equal to 0, dou square W by dou y square equal to minus a into pi square by b square into sin pi x by a into sin pi of 0 by b, which is equal to 0. Now, at y equal to b, we have dou square W by dou y square equal to minus a into pi square by b square into sin pi x by a into sin pi b by b, which is again equal to 0. Now, the function satisfies all the boundary conditions. Now, let us proceed to calculate the critical load. So, the total potential energy of the plate is given as the strain energy due to bending and the potential energy due to external loads V. So, let us look at the strain energy due to bending. We have U equal to d by 2 into 0 to b, 0 to a, dou square W by dou x square the whole square plus dou square W by dou y square the whole square plus 2 mu into dou square W by dou x square into dou square W by dou y square plus 2 into 1 minus mu into dou square W by dou x dou y the whole square into dx into dy. So, when we expand this one, basically taking the integral inside the brackets, we have this big equation as you can see on the screen. So, all the 4 integrals are divided as 1, 2, 3 and 4. Now, to evaluate this expression, the following derivatives are needed. So, W equal to a into sin pi x by a into sin pi y by b. We have dou W by dou x equal to a into pi by a into cos pi x by a into sin pi y by b. And dou square W by dou x square equal to minus a into pi square by a square into sin pi x by a into sin pi y by b. Similarly, we have dou W by dou y equal to a pi by b into sin pi x by a into cos pi y by b, and dou square w by dou y square equal to minus a into pi square by b square into sin pi x by a into sin pi y by b. And when we do double differentiate, we have dou square w by dou x dou y equal to a into pi square by ab into cos pi x by a into cos pi y by b. Now, when we substitute that in the first integral, we get 0 to b, 0 to a minus a into pi square by a square into sin pi x by a into sin pi y by b the whole square into dx into dy, and this can be written as a square into pi power 4 divided by a power 4 into 0 to b, 0 to a sin square pi x by a into sin square pi y by b into dx into dy, and substituting the definite integrals, which is 0 to a sin square pi x by a equal to a by 2 and 0 to b sin square pi y by b equal to b by 2. So, when we do so, we have a square into pi power 4 by a power 4 into a by 2 into b by 2, which gives rise to the value pi power 4 into a square into b divided by 4a cube. And the second integral is 0 to b, 0 to a dou square w by dou y square the whole square into dx into dy. Again, when we substitute it, we get an equation as you can see in the figure, and this can be written as a square into pi power 4 by b power 4 into 0 to a sin square pi x by a into dx into 0 to b sin square pi y by b into dy. So, we substitute the values a by 2 and b by 2 for the integrals, and we get the value pi power 4 into a square into a divided by 4b cube. So, now the third one is 2 mu into 0 to b, 0 to a dou square w by dou x square into dou square w by dou y square into dx into dy, and when we substitute it, we get a much bigger equation as you can see on the picture, and again it boils down to 2 mu into a square into pi power 4 divided by a square b square into 0 to b, 0 to a sin square pi x by a into sin square pi y by b into dx into dy. Again, when we substitute with the definite integral values, which sin square pi x by a becomes a by 2 and sin square pi y by b becomes b by 2, we get an equation as you can see here, which is 2 mu into pi power 4 into a square divided by 4ab. Now, let us look at the fourth integral, which is 0 to b, 0 to a 2 into 1 minus mu into dou square w by dou x dou y the whole square into dx into dy. We substitute the value of dou square w by dou x into dou y and we square it, and we get an equation here which can be further simplified. Basically, we have integral of 0 to a cos square pi x by a which is equal to a by 2 and 0 to b integral of cos square pi y by b which is equal to b by 2. And we substitute these values in the integral, and substituting that in the strain energy equation, which is given in the screen right hand side, we have the equation d by 2 into pi power 4 into a square b divided by 4a cube plus pi power 4 a square into a divided by 4b cube plus 2 mu into pi power 4 into a square by 4ab plus 2 into 1 minus mu into pi power 4 into a square divided by 4ab. So, we expand this one, we get two values that are shown in the brackets which can be cancelled, which is 2 mu by 4ab and minus 2 mu by 4ab. So, now let us multiply and divide with AB. We have this equation as you can see here, which can be further simplified as given as u equal to pi power 4 into a square into d into AB by 8 into 1 by a square plus 1 by b square the whole square. Now, that is the value for strain energy due to bending. Let us look at the potential energy due to external loads V. And the potential energy due to external loads V is given as V equal to minus Nx by 2 into 0 to B, 0 to A, dou W by dou X the whole square into dx into dy. And we know that Nx equal to N0 into 1 minus alpha into Y by B. And when we substitute these values here, we have minus half into 0 to A, 0 to B, N0 into 1 minus alpha into Y by B into dou W by dou X the whole square into dx into dy. The dou W by dou X is given as A pi by A into cos pi X by A into sin pi Y by B. So, we substitute this into this equation, we simplify this further as you can see here, and the simplified form is given here, which is minus N0 by 2 into A square into pi square by A square into 0 to A cos square pi X by A into dx into 0 to B 1 minus alpha into Y by B into sin square pi Y by B into dy. The first term is very simple, cos square into pi X by A is A by 2, but the second term actually has a function of Y. So, when we multiply that, we have in the integral 0 to b sin square into pi y by b minus alpha into y by b into sin square pi y by b into dy. Again, this sin square pi y by b can also be written as b by 2 because integral of 0 to b sin square pi y by b equal to b by 2. The integral that we need to evaluate is minus of 0 to b alpha into y by b into sin square pi y by b into dy. Let us look at this integral separately. So when we look at that integral separately, we need to use what is known as UV rule. Basically, u dv is equal to uv minus integral of v du. So here u equal to y and dv equal to sine square into pi y by b into dy. So this sine square can be written as 1 minus cos 2 pi y by b divided by 2 into dy. And this can be written as dy by 2 minus half into cos into 2 pi y by b into dy. This du equal to dy because u equal to y, and now when we integrate it 0 to b dv, so v equal to integral of 0 to b into half of dy minus half into cos of 2 pi y by b into dy. So this becomes y by 2 minus half into 1 by 2 pi by b into sine 2 pi y by b. Here we have to understand that when we integrate cos, the cos becomes sine, and then instead of multiplying we have to divide by the coefficient. So we have minus half into the coefficient is 2 pi by b, which comes down to the denominator, and cos becomes sine, which is just plus sign because integral of cos is basically positive sign. So sine into 2 pi y by b. So this value is given as y by 2 minus b by 4 pi into sine 2 pi y by b. So when we substitute that into this equation, we have 0 to b y into sine square pi y by b into dy equal to y into y by 2 minus b into 4 pi into sine pi y sine into 2 pi y by b bracket close 0 to b minus 0 to b y by 2 minus b by 4 pi into sine into 2 pi y by b into dy. So when we multiply this, we have y square by 2 minus yb by 4 pi into sine 2 pi y by b into 0 to b minus y square by 4, where the lower limit is 0 and the upper limit is b, minus b by 4 minus of bracket open b by 4 pi into b by 2 pi into cos 2 pi y by b bracket close. The lower limit is 0, the upper limit is b. So we can simplify this further, and finally we get the value which is b square by 2 minus b square by 4 minus b square by 8 pi square into 1 minus 1, which leads to the value b square by 4. So we have integral of 0 to b y into sine square pi y by b into dy equal to b square by 4. Now we can substitute this again in the potential energy equation V. When we do so, we get the value V equal to minus n naught by 2 into a square into pi square by a square into a by 2 into b by 2 minus alpha by b into b square by 4. So we can simplify this further, and we have a value V equal to minus n naught into a square into pi square by a square into ab by 8 into 1 minus alpha by 2. Again, alpha here represents the stress gradient that is acting across the width of the plate. So the total potential energy is defined as U plus V. So we have U plus V is given as pi power 4 a square d ab by 8 into 1 by a square plus 1 by b square the whole square minus n naught into a square into pi square by a square into ab by 8 into 1 minus alpha by 2. So we can have this one by taking the terms common, pi square ab by 8 into a square into bracket open pi square d into 1 by a square plus 1 by b square the whole square minus n naught by a square into 1 minus alpha by 2 bracket close. In accordance with the concept of neutral equilibrium and the principle of stationary energy, the critical loading can be determined by finding the slightly bent configuration for which the total potential energy has a stationary value. Basically, we have to differentiate that with respect to A, the total value U plus V. So we have dou of U plus V divided by dou A is equal to 0. So we have pi square into AB by 8 into 2A into bracket open pi square D into 1 by a square plus 1 by b square the whole square minus n naught critical by a square into 1 minus alpha by 2, which is equal to 0. Now we have this one, the term inside the bracket should be equal to 0. So when we do so, we have n naught critical by a square into 1 minus alpha by 2 equal to pi square d into 1 by a square plus 1 by b square the whole square. Now let's rearrange the terms. When we do so, we have n naught critical equal to pi square into d into a square into 1 by a square plus 1 by b square into 1 by 1 minus alpha by 2. Now let's multiply and divide with b square. So we have pi square into d into a square into b square by b square into 1 by a square plus 1 by b square the whole square into 1 by 1 minus alpha by 2. So we can simplify this further, and finally we get a value n naught critical equal to pi square d by b square into b by a plus a by b the whole square into 1 by 1 minus alpha by 2. In the previous classes, we have derived the generic equation for plate, which is simply supported along all edges with a uniaxial normal stress. So we have N naught critical equal to A by B plus B by A the whole square divided by 1 minus alpha by 2 into pi square D by B square. So the elastic plate buckling coefficient is given as K equal to A by B plus B by A the whole square divided by 1 minus alpha by 2. So the critical load is given as N naught critical equal to K into pi square D by B square. So for a plate simply supported on all 4 edges and subjected to uniaxial compression, we have alpha equal to 0, and taking a square plate A equal to B, we have K equal to A by B plus B by A the whole square divided by 1 minus alpha by 2. Since alpha equal to 0 and A equal to B, we have 1 plus 1 the whole square, which is equal to 4. So the elastic plate buckling coefficient is equal to 4. So N naught critical is given as 4 into pi square D by B square. Now let us look at another case where alpha equal to 1. So when we take alpha equal to 1, we have K equal to A by B plus B by A the whole square divided by 1 minus alpha by 2, so which is 1 minus 1 by 2, so we have K equal to 8. So the N naught critical is equal to 8 into pi square D by B square. Basically, when a triangular load is applied, which is 50% of the load of the uniaxial compression, the plate buckling coefficient value K actually doubles from 4 to 8. Now let's look at another case when alpha equal to 1 by 2. So when we have alpha equal to 1 by 2, the value of K is given as K equal to A by B plus B by A the whole square divided by 1 minus of 1 by 2 by 2. So when we do so, we get the value K equal to 16 by 3, which means that the N naught critical is given as 16 by 3 into pi square D by B square, which is equal to 1.33 times the plate that is subjected to uniaxial compression. So the moral of the story is, lesser the compressive load that is being applied to the plate, more is the plate buckling coefficient as it is reflected here. So when we apply 50% of the load, the K value jumps from 4 to 8, and we apply 3/4 of the load, the K value now jumps from 4 to 16 by 3, which is 1.33 times higher than the uniaxial compression. With this one, we have completed solving the critical load for plates using strain energy method. Thank you very much.